Welcome to Lesson 3-11B. Today we're going to look at theoretical yields versus percent yields. Theoretical yield is actually what we've been calculating this whole time based off of what our starting materials are. We added an extra element to it last time when we figured out what the limiting reactant was, and the fact that the limiting reactant was entirely consumed. We're going to add to that a little bit, and this will be the last adding to of this particular unit. We're going to look at percent yield. So percent yield is actual yield divided by theoretical yield times 100. So calculating a percent yield, methanol is also called methyl alcohol. It's the most simplest alcohol there is. It uses a fuel in race cars, potential replacement for gasoline, but it can be manufactured by combining gaseous carbon monoxide and hydrogen. So our dilemma is, suppose that 68.5 kilograms of CO, or carbon monoxide, is reacted with 8.60 kilograms, so obviously a very large scale reaction. We're going to calculate the theoretical yield of methanol, and then this is our number of grams produced, and we're going to determine what our percent yield is. So we're going to ignore this number until the very end because we have to calculate theoretical yield first. So where are we going? Calculating the theoretical yield, and then we're going to calculate the percent yield. What do we know? We know the chemical reaction because in the equation it said hydrogen is reacted with carbon monoxide to produce methanol. And we know how much of each of the starting products we have. We know how much methanol is produced. So what do we need? We need a balanced equation. We need to know how many moles of hydrogen gas we have, how many moles of carbon monoxide, which one of those is limiting, the amount of methanol produced. And how are we going to get there? We have to balance the chemical equation first. So the only thing we need to do was add a 2 in front of the hydrogen. So again, I encourage you to stop the video and balance that equation on your own. How many moles of hydrogen and carbon monoxide do we have? There's the molar masses. Notice again, hydrogen is diatomic, and so we take 1.008 times 2. And then carbon monoxide, we add the carbon mass to the oxygen mass. Okay, so first off, let's look at carbon monoxide. This is the prompt given to us by the problem. We need to get it into grams, so we're going to use this unit factor to get it to grams. Notice we need kilograms on the bottom because we need that to balance out. We need grams on the top. Now, a lot of times students can't remember where the 1,000 goes. They know there's 1,000 of something in there. Just know that the bigger number will go with the smaller unit. So grams are smaller than kilograms, so the 1,000 goes with the grams and the 1 goes with the kilograms. Next step, we'll use the molar mass to get to moles, and so this is how many moles of carbon monoxide we have. We're going to do hydrogen the same way. We have 8.6 kilograms of that, convert it to grams, use the molar mass to get to moles, and we have 4.27 times 10 to the third moles of hydrogen. Now that's how many moles we have. We need to determine which one is limiting. And what we're going to do is we're going to use each of those moles that we just calculated and use the balanced chemical equation to figure out how many moles of methanol we would get if they were able to react completely. So if we reacted 2.44 times 10 to the third moles of carbon monoxide, we would get 2.44 times 10 to the third moles of methanol. If we react 4.27 times 10 to the third moles of hydrogen, because it's a 2-to-1 relationship in the balanced equation, we would only get 2.14 times 10 to the third moles of methanol. So which one of these is a smaller number? They both have the same magnitude on the tens place, so this one is a smaller number. So this right here is our limiting reactant. So hydrogen is our limiting reactant. We have the moles of methanol. We just calculated that. What's our theoretical yield? So we're going to take those moles and we're going to use the mass, the molar mass of methanol, to figure out how many grams of methanol we would obtain from that reaction if it went to 100% completion with that limiting reactant. So that's our first answer. That's what our theoretical yield of methanol is. our percent yield. So in our problem, in our prompt, it said this is how much we obtained. So that was our actual yield divided by our theoretical yield times 100, and it gave us 52% yield. And that's actually a very high yield for a synthesis reaction. So when you need to solve a problem like this, you need to write and balance an equation. You need to convert the masses of substances to moles. You need to determine which reactant is limiting. Once you know which one's limiting, you can figure out how many moles of product you will get, and then you convert the moles back to grams using the molar mass. So let's do a few conceptual type questions. In the reaction 2A plus 3B, if I have gives you C. If I have 4.0 moles of A reacting with 4.0 moles of B, which of the following choices best answers the question which reaction is limiting? Neither is limiting because I have the same amount, and remember, it was 2A plus 3B gave me C. So neither is limiting? No, one of them has to be limiting, because if I have 4 moles of A, how many moles of B should that react with? Should react with 6. So A is limiting because 2 is smaller than 3. No, not because 2 is smaller than 3. A is limiting because 2 moles is available but 4 moles is needed. That's not correct either. B is limiting because 3 is larger than 2. And that is correct because I would need 6 moles of B to react with 4 moles of A. I apologize. E is correct because B is limiting because 4 moles is available but 6 moles is needed. My apologies on that one. Limiting reactant in a reaction has the smallest coefficient. That's not true because in that last reaction, 2A plus 3B gave me C. That A had the smaller coefficient, but it wasn't the limiting reactant. The limiting reactant is the reactant in which you have the fewest number of moles. That's not always true either. Has the lowest ratio of moles available to the coefficient, or has the lowest ratio of coefficient in the balance equation to moles available. And this was going to be correct because if it has lower moles available, then it's going to be the limiting reactant. Which of the following reaction mixtures would produce the greatest amount of product according to the following chemical equation? So the equation was 2 moles of hydrogen plus a mole of oxygen gave me 2 moles of H2O. If I have 2 moles of hydrogen and 2 moles of oxygen, how many moles of water am I going to get? I'm going to get 2. If I have 2 moles of hydrogen and 3 moles of oxygen, I'm still only going to get 2 moles of water. If I have 2 moles of hydrogen and 1 mole of oxygen, which is the exact stoichiometric ratio, still going to get 2 moles of water. If I have 3 moles of hydrogen and 1 mole of oxygen, now this is limiting because I don't have enough hydrogen to react with it, but I'm still only going to get 2 moles of water. And so all these choices are going to produce the same amount of product. Now I know some of those questions there at the end were kind of confusing, and I apologize for adding to the confusion. But please note that the mathematical part is the more important part, so make sure you get plenty of practice with percent yields and theoretical yields.